Thank you very much for the introduction, and thank you very much for the invitation. So I'm sorry for the very long title. And actually, I will start with something slightly more general. So it didn't even work to put every result in the title. So this is based on a recent joint work that I have done with Louis-Pierre Chantron and Giovanni Conforti. And we will start with a small warm-up on propagating log concavity, and so that you understand how we want to generalize it. And I want to talk about two consequences today that are specifically interesting for the audience here, which is Lipschitz transport maps and convergence results on Sinkhorn's algorithm. So let's start with a quite classical result by Braskamp and Lieb. So if you take kind of a generalized heat operator where you have the Laplacian and the multiplicative operator given them by a potential V, and you start with something with a uniformly log concave initial condition, and your potential V is supposed to be convex, then Braskamp and Lieb showed that log concavity is preserved, and you can even give a formula in a way on how this log concavity, this uniform log concavity behaves in time. So this is already a very nice result. However, you see that as soon as kappa is negative, actually this estimate is still true, but it explodes in finite time. And it is not because the estimate is bad, it's actually sharp for Gaussians. So there's not much more you can do in the uniformly convex case. Another result in the same spirit is if you now take another heat operator, which is actually the dual of the Langevin dynamics, and you want to propagate log concavity in a similar way. So you suppose your initial, oops, I should maybe use the pointer for the people. So you start with a log concave initial condition, and you want log concavity to preserve. Then it is known that this is only possible if your potential U is quadratic. So if you're associated to Ornstein-Uhlenbeck dynamics, which is a bit disappointing because one would like to have a preserving property for more general dynamics. And this is why I will introduce a weaker notion than semi-convexity, which we call weak convexity. And it's a bit more technical, but I hope from the examples you see that it's kind of necessary if you want to push the theory of propagating notions of convexity further. So in order to introduce the weaker notion of convexity, let me just recall one of the equivalent formulations of semi-convexity that we have, namely your potential V is kappa semi-convex. If you have the following inequality uniformly in X and Y. And you have some kappa that satisfies this inequality. So this is the usual kappa semi-convexity. The way we generalize it is we don't require there to be a uniform kappa to satisfy this inequality, but a kappa that depends on the distance of the 2 points. So now we have a bound on the scalar product between the gradients at the points, which is uniform in all X and Y, which are at the same distance R. This generalized modulus of convexity can be, if you rearrange terms, can be written as the infimum of the following fraction. So this is just a simple rewriting. And to give you maybe a bit more idea about this kappa, if you do a Taylor development of order 0, you see that the kappa is also given by the infimum of an averaged integral of the Hessian. So in a way, instead of having a lower bound on the Hessian pointwise, you look for a lower bound on an average sense of the Hessian. This is kind of the convexity profile. Moreover, if you let R go to 0, you will converge towards the lowest eigenvalue of the Hessian of all the points. So you recover classical convexity bounds with this modulus, but it contains more information because you really measure for all the distances of the points. So is there a question to this modulus of convexity? Because it will stay with us the rest of the talk. Namely, if you now try to understand how does this modulus of convexity propagate along these flows, I will show you the theorem now. So, yes.
For the diffusion, there any reason why you want to keep the equality for the
You mean here? We really would like to include all the points that are at this distance. Ah. I think that if you take smaller equal to r, then you will always basically take this limit immediately, and so the interest will be also, it was hidden in the title, I also want to be able to treat potentials that don't have a Hessian. So if I fix the r for r positive, this is also well defined if I don't have a Hessian, but if I would take smaller equal than r, I would run into problems. No, it depends on the potential. Okay, so the main result that we had in the paper with Louis Pierre and Giovanni is the following. You take a very general heat operator, and then you take a function f of the radius r and of time, and you suppose that it satisfies this PDE, which, if you ignore the last term for now and you take equality, is essentially a Burgers equation. So you have a Burgers equation with a certain source term that I will talk about later. If your f at time 0 bounds the convexity profile of the u, which is the drift term, minus the log of phi 0, so that would be the initial condition. So if you have some kind of common convexity bound on the initial condition, then your ft will bound the convexity profile of your solution at every time. Okay, this may seem very technical, but we will see an example just in the next slide. Just one last comment on this source term. So the A of u is the so-called reciprocal potential, and it is a potential that appears when you do second order, when you look at kind of the Newton equation related to this problem. So in a way, the second order equation of this problem governs how the convexity evolves. And this is also why usual convexity works really well, because in this case, the AU will just be again quadratic. So you have this preservation of usual convexity, but in the general case, you need to understand the convexity modulus of this potential. So if this was too much, fear not. Let's revisit the example by Braskamp and Lieb in the language that I've just introduced. So we are back to the heat equation with a Laplacian and a multiplicative operator. We are in the classical convexity case. And our ft now will be given by kappa over 1 over kappa t times r. And you see now, through the lens of Burgers equation, this is a classical solution to the inviscid Burgers equation. So there's no diffusion term. And if you do the computation, you see that it satisfies our Burgers inequality that I've shown you just before, because this function is linear, so there is no Laplacian term, and the source term is just positive. So we satisfy our Burgers equation, and we can conclude that the convexity profile that propagates along the heat flow, a generalized heat flow, is given by ft. And if you now want to translate it to the actual lower bound on the Hessian, you can do so by just taking the limit of r going to 0, which corresponds to ft over r, and which is exactly the bound that we had from Braskamp and Lieb. So with our formalism, we recover the classical propagation of convexity that it was known in the literature. But I hope that here you can see that actually the result by Braskamp and Lieb does not use the diffusion term at all in the propagation of convexity. But in our formalism, we have the diffusion term, and we are going to make use of it to create log convexity along the flow. eventually. Questions? Or okay, I will continue. So with that in mind, let me give you the definition of the generalized weak convexity that we will look at and that works well. So here I just recall to you the definition of the modulus of convexity that we have associated to V. And instead of supposing uniform convexity on V, what we have done before, our framework works for what we call asymptotic convexity. And asymptotic convexity means that if the points are very far, the convexity profile should look uniformly convex. So the modulus of convexity should become positive if the points are very, very, very far. And moreover, the negative part of the convexity profile times R should be integrable, meaning that we should not violate convexity too much. So yeah, it's a bit technical in this part, but really imagine, let me give you some examples on potentials V that satisfy these conditions. So obviously, if V is just a uniformly convex function, our convexity profile would be bounded by alpha, where alpha is the uniform convexity constant, and it satisfies asymptotic convexity. But you can also think about V plus some Lipschitz functions. In this case, the convexity profile would be of the form alpha minus L over R. So it would satisfy our requirements for asymptotic convexity. And I drew you some pictures of examples of asymptotic convex potentials. The important part that if the points are far, it should again look like a convex potential. Okay, so far for the technical part. For now, what is important for you is that under these conditions of asymptotic convexity, I will prove two things today. I will prove that you can construct a Lipschitz transport map from the Gaussian measure. And I will also tell you some application to Sinkhorn's algorithm. Oops, sorry. Let me briefly introduce you to Lipschitz transport maps. So the goal is you're given two measures, rho and nu, and you want to find a map between them. So m push forward rho should be equal to nu, and m should be Lipschitz continuous. The reason why we are interested in this is basically two main reasons. If your measure rho is regular and satisfies some nice functional inequalities, thanks to the fact that you have a Lipschitz transport map, you will transfer these functional inequalities to the measure nu. And of course, you're interested that the Lipschitz constant is as small as possible, ideally independent of the dimension for this to have be a meaningful result. And the other one is that if you have a regular map, it also helps you for statistical guarantees. We've already seen in the morning that having a Lipschitz transport map helps with stability issues and estimation issues. The first way to get a Lipschitz map would be, of course, to take the map coming from optimal transport directly. And this was also historically the first map that people have looked at. So there's the seminal work by Caffarelli, which says that if you start, so it's a simplified version, but if you start from the Gaussian measure and you transport on a uniformly log-concave measure, then the optimal transport map is Lipschitz with a very nice constant independent of the dimension. And this is very nice, but it is very difficult in general to prove regularity of optimal transport maps. There has not been many advances in this case. This is why, if you think about the applications we have in mind, you don't really need optimality of the transport map. You just need a transport map which is as regular as you want. And this is why Kim and Milman have thought about defining a different transport map coming from diffusion processes. So here you just take, and I will explain to you their construction. So basically you take the Langevin dynamics, starting in the measure nu, and in optimal transport terminology, you can rewrite this diffusion equation as a pure continuity equation, where your drift term is given by the time-dependent potential Vt, which is minus the log of the Radon-Nikodym density. And so by pure nature of the continuity equation, you will get a transport from the initial measure nu to the solution μt of the measure. Namely, you can associate a deterministic ODE to this equation. And you know that if you start x bar 0 in nu, then the law of x bar t will be equal to μt. And you can translate that in a transport map by defining the following family of maps. So, oops, sorry. ST satisfies the same ODE, and its initial condition is just the identity map. And then you can prove easily that ST push forward nu is equal to μt. And so if you suppose that everything goes well in the end, it will, under the assumptions I give you, it will converge to a map S infinity pushing forward nu to rho. Here I should mention that the measure rho is proportional to exponential minus u. So this is really, I use the Langevin dynamics, which should converge to rho in the end. And if you invert the map, you get exactly what we want. You get a map from a nice regular measure rho to the initial condition, which we can choose arbitrarily. Now, the conditions, oops, sorry. The conditions to verify so that M is Lipschitz are also readily available thanks to Mikulinza and Schenfeld. Namely, the art is to have bounds on the eigenvalues of the time-dependent potential Vt. So if you can lower bound and upper bound the Hessian of Vt, you get that the forward map S infinity will be Lipschitz constant with this constant, and M will be Lipschitz constant with this constant. And I think it is very instructive to just see the sketch of the proof. It's essentially a Gronwall argument. So you just observe the ODE satisfied by the gradient of ST. And you see that if you want to bound uniformly the gradient of ST, you just do the ODE, and you see that if you have a bound on the upper eigenvalue, you can just conclude with the Gronwall argument, and you get the bound on the Lipschitz constant. And the same goes the other way for the map M. So the moral of the slide is we want to have, like, especially for the map M that we're interested in, we want to have low bounds on the eigenvalues of the Hessian. And we can do that using the Burgers inequality that I showed you in the very beginning. Under the following conditions. So here is what we want, just a brief recall. We want to transport from the Gaussian to some measure nu. And we want this map to be Lipschitz continuous. So in this case, the Langevin dynamics corresponds just to the Ornstein-Uhlenbeck process, a very simple one. And we managed to prove that if the W, which is minus the log density, is asymptotically convex. So this included uniformly convex plus Lipschitz perturbations, etc. Then the diffusion transport map by Kim and Milban will be Lipschitz continuous. And moreover, this constant will be independent of the dimension if the way we violate convexity, so the negative part of the convexity profile should be integrable, and this constant should be independent of the dimension. And that's all we need for the constant to be independent of the dimension. And the proof goes essentially as follows. The driving vector field is given by the time-dependent potential V, and we can track the convexity profile, now in the usual sense, the semi-convexity of Vt, with the help of our weak convexity profile, kappa Vt. Okay, and because if you are dealing with Lipschitz transport maps, it's always nice to see the constants. So let me just show you, if you do the computation with Burgers equation, what does the what is actually a lower bound on this lambda mean of EVT. And in order not to overload you with constants and so on, we just do a rescaling in time and space to get from the Ornstein-Uhlenbeck process to just a simple heat equation. And then the initial condition is just slightly modified. So if W was the minus log density of the initial condition, and we just subtract the log density of the Gaussian. And in this case, if you take now minus the log of phi t, you see that the convexity profile in the classical sense now is given by the first term. This is the term that we have already seen in the Braskamp-Venditti result. So we suppose like asymptotic convexity with a term alpha. And then the second part of the estimate comes from the fact that we are not classically convex, but we have a perturbation. And it is essentially this term here minus the second moment of a random variable. And this random variable has a density, which is explicit, but maybe a bit ugly because we are in a very general case. It's essentially the product of a Gaussian density times exactly this violation of convexity that we have seen all the time. And then if you just, after this rescaling, you see that the Lipschitz constant will be given by exponential of minus the integral between 0, 1 of this quantity. And you see very well, if we would not violate convexity, then this would be well defined everywhere. If not, you need to work a bit because the 1 over t is, of course, not integrable on 0, 1. But it turns out that under these asymptotic convexity conditions, this will be always integrable and give quite nice constants. Just to give you a more approachable example, I've done the computation for you in the case where our potential W is the sum of something uniformly convex and Lipschitz functions. In this case, you can compute the integrals and you get quite a nice formula where, again, you see because the initial condition is not twice differentiable, this estimate will, of course, explode as t goes to 0, but it is integrable on 0, 1. And let me just remark that this, for the case of Lipschitz perturbation of uniformly convex functions, this is not new. It has been proven last year by Brigatti and Pedrotti, and we get quantitatively the same constants as them. We just have slightly better multiplicative constants. And so this closes the part about Lipschitz transport maps. The next part is about entropic optimal transport and convergence of Sinkhorn's algorithm. So you should be familiar with it, but let me introduce the notation. So the entropic optimal transport problem, given two measures rho and nu, is basically minimizing the cost that you know from quadratic optimal transport plus an entropic regularization, and you minimize among all couplings between rho and nu. Optimal solutions are unique and characterized by this Gibbs-like distribution, where u and nu are the so-called Schrödinger potentials, which solve the Schrödinger system. So essentially, you see that they are like minus log of the heat semigroup. So you can already guess where we are going with this. And the way you compute optimal transport plans is you iterate between the Schrödinger systems and you hope for the potentials to eventually converge. So this is the spirit of Sinkhorn's algorithm. You start with one of the potentials, you update the other one, and you iterate in a way. And at each iteration, you get an approximate solution of entropic optimal transport plans. And then the question is, how fast does this approximate solution pi n plus 1 n plus 1 converge to the true entropic optimal transport plan? And there has been a really nice result from 1 year ago by Giovanni and his collaborators, which says that if your cost function minus the one of the iterates of Sinkhorn's algorithm is semi-concave, and uniformly in X and in the iterations, and nu satisfies a Talagrand inequality, then one can prove that the convergence rate of Sinkhorn's algorithm is exponential. So there is a lambda smaller than 1 and scales to the power lambda and in the iterations. So I wanted to make one remark. Do I still have 5 minutes? Oh, 10, awesome. Okay, maybe I don't even need all of them, but thank you. So, okay, but then I can take some time for this remark to translate this semi-concavity property in the context of stability of optimal transport. So by semi-concavity, I mean that the Hessian in Y is basically bounded from above. If you were to imagine that the second term is basically a Kantorovich potential, so I wrote it here in gray, you develop the square, and then if you were in the optimal transport setting, this would correspond to something linear in Y plus the Brunner potential in Y. So assuming that this quantity here is semi-concave corresponds to having a Hessian bound on the upper bound on the Hessian of the Brunner potential, or a Lipschitz continuity of the transport map. And you have heard in the morning, again, that there is this famous result by Gili that precisely in this case, you have a nice stability property in optimal transport. So this is nice, but we also know that it's in optimal transport, it's rarely satisfied if you're outside of the uniformly convex setting or don't have nice measures on the compact case. So the point I want to make, it is natural that this is a condition you would expect to have, like stability in the entropic optimal transport setting and convergence of Sinkhorn's algorithm. And the good part is that in the entropic optimal transport case, it is much easier to be satisfied. Namely, it will be satisfied by all the measures which are asymptotically convex. So for this, let me rewrite the iterations of Sinkhorn's algorithm in the language of my heat semi group. So Vn is essentially minus log of phi epsilon, where phi t satisfies, again, the heat equation, and the initial condition is suited to taking the previous iterate plus the times rho, essentially, where rho is one of the marginal measures. And so you can readily check that the UN will not be too nasty along the iterations, and log rho, we have supposed it to be asymptotically. If we suppose log rho to be asymptotically convex in the sense I've shown you, you can prove from the creation of semi-convexity that I've just shown you that this functional will indeed be semi-concave in a way that we need it for Sinkhorn's algorithm to converge. And in particular, if you choose both measures to be asymptotically convex, you get 1, the semi-concavity of this cost, and 2, you get Talleyrand inequality because we have a Lipschitz transport map towards it, which justifies that it satisfies Talleyrand inequality. So this was just a main remark that we can extend basically exponential convergence of Sinkhorn's algorithm for these asymptotically convex functions. And since I have 10 minutes, I can show you also the heavy slide of the proof sketch of the result in the very beginning, which was convexity profiles propagate along Burgess type equations. So the proof is hopefully in the spirit of this conference as well. So we use that minus log of phi t, which is like a Hopf-Kohl transform, satisfies a HAB equation, which has a stochastic representation in form of an optimal control problem. For this optimal control problem, we look at Newton type kind of equations, so the BSDEs associated to it. And we couple 2 solutions of them via what is called coupling by reflection. And if you're used to coupling by reflection, you know that this convexity profile naturally appears in this kind. And we managed to prove that if you want a function f to approximate the convexity profile in a good way, this is possible if your f satisfies this Burgess type equation. So it pops up naturally in the computation that if ft lower bounds the convexity profile in the beginning and satisfies the Burgers equation, then it will lower bound the convexity profile at every time step. So this is very nice. And the remaining part is essentially analysis of the Burgers equation to conclude. And with that, thank you for your attention.